Okay, let's dive into this. Physics, for, well, almost a century now, has had this kind of split personality.
Yeah, it's pretty fundamental. You've got Einstein's general relativity.
Right, the theory for gravity, stars, galaxies, the really big stuff,
Exactly. And then on the other hand, there's quantum mechanics.
which handles the tiny world, atoms, particles, all that quantum weirdness.
And both theories work incredibly well, I mean, amazingly well, in their own domains.
But they just don't mesh, do they? Especially on, well, on the nature of time itself.
That's a big one. GR says time is relative, flexible, part of space-time that gravity can bend.
Well, quantum mechanics, at least in its standard form, treats time more like a fixed background clock. Absolutely.
Right, and that clash, it becomes a serious problem when you need both theories at once. Think about black holes or the Big Bang.
Situations where you have massive gravity and tiny scales. So physics needs a bridge, right? A theory of quantum gravity.
That's the holy grail, pretty much. Figuring out if gravity itself follows quantum rules.
Yeah.
But getting experiments to test this, that's been the bottleneck.
Because the energy needed to see gravity act quantumly, the Planck scale, is just astronomical, way beyond our particle collider.
Exactly. And that's why this MIT experiment we're looking at is, well, it's generating buzz. It's a totally different approach.
A tabletop experiment, you mean? Not a giant collider.
Precisely. They're trying to see if gravity can exert a quantum influence, not by smashing things together, but by getting relatively large objects.
Macroscopic objects, things we can actually see and touch.
Well, almost. Centimeter scale.
Yeah.
Getting those objects to behave quantum mechanically first.
Okay, so how do they do that? What's the core device?
It's called a torsional oscillator. Picture a small bar or disc hanging from a really thin fiber, twisting back and forth.
Huh. Sounds kind of old school, actually. Didn't Cavendish use something like that centuries ago?
He did. To measure gravity, weigh the Earth, basically. It's a classic tool for sensitive gravity measurements.
So using a classical tool for a quantum question, that's neat. But the challenge must be immense. Gravity's so weak at that scale.
It is. And quantum states are incredibly fragile. So you need something, as you said, massive enough to feel a gravitational pull, but also quiet enough.
Quantum quiet. So its own quantum behavior isn't drowned out by just random jiggling.
Exactly right. And getting it that quiet is the first big step. They borrowed techniques from atomic physics, actually.
Like laser cooling. I thought that was just for atoms.
Usually, yes.
Yeah.
But they adapted it for the first time to cool one of these torsional oscillators. And they got it down to 10 millikelvins.
10 thousandths of a degree above absolute zero.
Just about. Incredibly cold. Because heat means vibrations, thermal noise, which would just swamp any subtle quantum effect.
So cooling gets rid of the thermal noise. Does that get it into its quantum ground state?
Not quite the ground state that's the absolute lowest energy possible. But 10 milliKs is extremely close. It suppresses the thermal noise so much that the oscillator's own quantum fluctuations, its zero-point motion, become a dominant factor. It's a huge step.
Okay, so it's cold enough to potentially see quantum effects, but measuring those tiny quantum jiggles must be another nightmare.
Oh, absolutely. You need incredible precision. They used a very clever optical lever system, basically bouncing a laser off it.
But lasers themselves aren't perfectly stable, are they? They jitter.
Right, that's the problem. Laser noise could easily look like the oscillator moving. So their setup uses two laser paths. One measures the oscillator, the other acts as a reference.
Ah, so they can subtract the laser's own wobble?
Precisely. And it works brilliantly. They canceled that noise by a factor of 1,000.
1,000 times less noise. Wow.
Which lets them measure the oscillator's position with precision, nearly 10 times better than the size of its own quantum zero-point fluctuations.
So they're measuring below the quantum fuzziness level.
Effectively, yes.
Yeah.
It's what physicists call a quantum-limited measurement. They're right down at the fundamental limits set by quantum mechanics itself.
Okay, so they've shown they can cool this thing way down and measure it at the quantum level. That's the proof of principle. What's the end game?
The ultimate goal, the really exciting part, is to use two of these oscillators. Prepare both of them in these near-ground quantum states.
Two oscillators?
Place them close to each other and see if gravity alone can link them.
Link them how?
Quantumly. See if gravity can cause them to become entangled.
Ah, entanglement. Einstein's spooky action at a distance. If gravity can do that.
It would be incredibly strong evidence that gravity itself must be a quantum force, that it participates in quantum phenomena, mediating entanglement.
So this tabletop experiment could potentially show gravity is quantum. Why should you listening care about that? What does it change?
Well, fundamentally, if gravity is quantum, It unlocks the path towards a unified theory combining gravity with the other forces. It can help us understand the singularities and black holes, or what really happened at the moment of the Big Bang.
Mysteries that current physics just can't crack.
Exactly. And even if they don't see entanglement, that result is also hugely important. It would challenge our assumptions and force us to rethink things. Plus, the technology itself.
Right. Cooling massive objects like this, measuring things with such insane precision, that has to be useful elsewhere.
Oh, absolutely. Think better sensors, quantum metrology, maybe even new materials research. The technological spin-offs could be significant.
So it really shows how these, well, relatively small lab experiments can tackle the biggest questions out there. Questions we thought needed maybe galaxy-sized experiments or huge colliders.
It's a shift in perspective, definitely. Makes you wonder, doesn't it?
It really does. What other huge cosmic secrets might just be waiting for the right experiment, right here on a lab bench?